Today I am going to present numerical simulation and experimental optimization of mining industry structure, vibration, and assessment of associated natural frequencies. In the next slide, here the table of content. I will discuss introduction, objective, monitoring and ground vibration, some other data recording, essentially regulation of vibration, analysis of recording data, analysis of structural response, numerical analysis, and conclusions. Basically, mining industry, they have a lots of mining vibration, ground vibration generation, like is the blasting, and there are lots of heavy machineries are used there. So we are discussing here machineries like ore processing units. Like here is a one place, Jamadova coal mines at Tata Steel. So we'll discuss on that ground vibration generation, and in every structure has its own natural frequency. If the another frequency collide with the natural frequency, it will be the resonance, and that resonance will be impact on the structure or the building. Not only the mine industry, it can be earthquake, it can be another sources of ground vibration generation. So this is the whole study focus on the numerical and experimental assessment of such the vibration Jamadova coal preparation plant, which is situated in Jharia coalfield, Tata Steel. So in next slide, here is our objective to measure the analyze of ground vibration generation in the different unit of Jamadova coal preparation plant, and to study the structural response nearby the buildings, and to develop the numerical models using the finite element methods and predicting the vibration behavior under the different soil and structural conditions. And another thing is recommend the effective vibration control measures based on the experimental numerical results. And last one is the develop and the validate the finite element method of the dynamic response simulation. So in the left side you can see the plan view of the Jamadova coal mines. So here the Jamadova washery plants is there. They are coal, and then you have lots of washery plants are there. They will generate a ground vibration, and then the residential buildings are there. So in the next slide, you can see is a monitoring of ground vibration. We have to pick seismograph, and which have a triaxial geophones, which are recorded the three channels, like first transverse, longitudinal, and vertical. So you can see the pictures of Jamadova coal washery plants. In the next slide, here is a summarized data of vibration recording. We have to record. You can see the measurement location, distance, and summarize the PPV data and mode of frequency. So in this table, the minimum frequency, the minimum vibration we have measured 0.132, and then maximum vibration we have recorded 2.854 mm per second. And then there is in this table there is one similarity. So you can see the mode of the dominant frequency, which is the nearly 14 Hz. So I will discuss further why it nearly comes from 14 Hz. And here is some statutory regulation on vibration. So first is the J building vibration criteria. This is all the criteria discussed on the PPV mm per second. So in there is a table 2 is the Swiss association, and corner vibration criteria, weapon vibration criteria, downing building structure vibration criteria is there, and also maximum vibration is level preventing the damage. And next is one is there is a California Department of Transportation also given us some criteria based on the vibration. So there is one statutory regulation on the vibration according to DGMS, which are given the frequency but not given the natural frequency of the regulation statutory. And there is also vibration, human perception of motion, and there are another also given the vibration criteria is there. So we have analyzed all those data, and we have found that the plot, there is maximum vibration we have generated. We have found that under the belt of CV80, and you can see in the right side there is a plot between the dominant frequency and the distance. You can see there is a major frequency lies between the 12 to 18 Hz. So in next slide we have the assessment of the ground vibration predictor equation. We have developed a predictor equation by the USDM predictor equation, and we did the 95% over the 95%, and the mean of 50%, and above the 95%. So here the assessment of ground vibration predictor equation. We have SS, and you have to predict what will be the upcoming vibration will be happen. So by the predictor equation we have developed. And in this assessment, we have the assessment with the correlation predictive PPV and threshold vibration human responses. So you can see here there are some PPV, they have threshold perception, and there are some barely noticeable, troublesome, and severe condition was there. And so finally here is structural response of two ground vibration. So you can see two pictures in right side. First is the structural vibration monitored at DMS plant, and another is ground vibration monitored at DMS plant. So we have to fix the one geophone is ground surface, and one fix the upper of the surface level. And we have measured the response of ground vibration. So you can see in the next slide. Here is our data we have recorded. First is ground vibration. We have recorded PPV in terms of mm per second and dominant frequency in hertz. And another one is structural vibration. PPV in mm per second and dominant frequency is there. So here is the plot of transfer function recorded the structural vibration with the Bernard Tombolici house. There is one house is there. We have to measure that particular house, and we have seen we had two examples. First in DMS plant, and another one is one of our near to the industry is one person Bernard. So we have measured and we have seen. You can see there's two arrows here. Is in the left side there has here arrows is showing the natural frequency of the structure which is caused resonance in the 14.69 hertz. You can see in the green color which have a different type of resonance band is there. In the right side the frequency arrow is showing the resonance of the structure 24.94 hertz, which is not a resonant because of if the frequency will be lies on the same frequency, it will be a resonant. That's it. And I done numerical simulation in the response spectrum. So response spectrum analysis determined the vibration amplification under the transition which have a deformation. So we have analyzed the initial frequency by the deformation. So you can see here figure A, resonant frequency between the 7.19 hertz, 24.181 hertz. Which one you can see there are lots of deformation in the bottom of the ground, which is red color. And other side is a figure B, resonant frequency between 24 hertz or more than that 24 hertz. You can see there is no deformation in the structure, and also the ground. And also I have done a model analysis, which have model analysis revealed dominant natural frequency within the range of 14 to 25 hertz. Field recorded resonance frequency, because higher frequency shows a localized deformation. You can see here they are localized means that the surface of the ground they have a deform. But if the less than 14 hertz, it will be impact on the structures. So here also I have modeled harmonic response analysis, and you can see here harmonic citation applied within the 2.5 to 25 hertz range shows the significant deformation amplitude nearly 14 to 18 hertz. Response plots indicate the structural amplification at the resonance band. So here is our conclusion. So conclusion is ground vibration monitoring at JCPP, Jamadova Coal Preparation Plant, shows the PV value is less than 0.12 and 0.85 mm per second. Within dominant frequency is 8.18 hertz. Mainly CAT belt and DMS plant have shows the resonance area. And the resonant in effect near 14.25 hertz, which caused the structural amplification. And that's also a natural frequency, and especially the Bernard Tomboli house within the 132. Huge impact on that particular building because of the collide with the same frequency. And we have I have analyzed all the models we have created and analyzed all the resonance factors. And here is a reference. And
so Manish,
yes, sir.
so I have a couple of questions that clarifications from your side. So basically, correct me if I'm wrong. So what I understand is, so basically you have used the data, vibrational data from a coal preparation plant, and you have tried to evaluate the impact of the vibrations in a nearby house. So and then you have used that data to model or simulate how the vibrations are affecting that particular building. And you have shown that for different frequencies, whether the vibrations are concentrated or it is present going to the building. So how do you plan, like from a future work perspective? So how do you plan?
This is a part of like research. Right? This is a little part. Like I have planned part of vibration due to blasting. Then if you go in the
blasting.
Yeah, if you go see the blast. I'm a mining engineer.
Right.
My BTech mining engineer. So if you saw the blasting in open cast, they huge mass of vibration generation. And if the same type of frequencies matches, they have collided with the story of building they have impacted on.
Right.
So I will look into this. This is just a little part.
Right. But how do you plan to utilize this data, and like how do you plan to help the industries with this data? That in order to incorporate like vibration mitigation strategies, like, is that the plan?
Sure,
I'm
sure.
just curious. Like, what is your understanding?
So every plants have a same type frequency generation. Frequency we can't see because of
Correct.
soil media we can't dependent on us. So if we can report by different industries, like if there is some mines there, some plants are there. So this particular area have a different type of initial frequency for particular structure. So we have to just first calculate that particular area, and we know that frequency is 14.56, and then we have to fix the regulation. That if you make any buildings in around this or any nearby the structure plant, you can fix that type of condition of building. If you not make, you will you feel resilience. If you make according to that criteria, then you can be safer for that upcoming vibration.
So basically, you can help the civil engineers
Yeah, civil engineering.
construct buildings which does not match with that particular resonant frequency of the
Yes.
last whatever vibrations are created in and around that industry.
Yeah, that's it.
How do we measure the resonant frequency of buildings? Let's say this building.
Resonance frequency.
So how do I measure it?
Sir, we can measure by the amplification, how much amplified the value. Like we can measure by in the bottom, in let's suppose 3 mm per second. But in the upcoming stairs, it will be any higher, it will be resonant like 6 to 7 times. We
Now,
have
when you're telling the values, I'm asking how do you know that it is 3, not 2.5?
how, sir?
How?
Like by the help of sensors. Sir.
By the sensors are there, right?
Yeah, we have sensors. Sir. Like they have a 6 channel of seismographs. Like we have the fix in the ground, one fix in the surface, and if the vibration just come, first analyze like bottom, and then this is field, and then after there's some more, and then it will reach after some structure, and that point, the second sensor, that will be calculated how much amplified the value.
And see, you're trying to model, you're given 3 equations now.
Yeah, yeah.
So I understand that with those equations, you can figure out how much vibration is going to happen at a certain spot, let's say 10 kilometers from this.
Yeah, if you mean distance relation.
It's a function of distance.
Yeah.
Correct.
Yes.
And that expression, how do you come to that? Like you have some data points.
Sure.
Now you try to put some formula which kind of satisfies all these data points. That is one mechanism.
Sure.
Or secondly is like you have taken some data driven method and then some AI/ML help, and then you are trying to come up with some.
Yeah, we can put the random. I have done a random forest to predict what will be the frequency will be in upcoming like 1 story building, 2 story building, 5 story building. I predicted in random forest.
Okay. And you have come from Nice and Ganga.
Yeah.
When did you arrive here?
Yes, sir, for 9
Okay. Thank you.
So the next speaker is Olimpa Baro, and the title of the talk will be Porous Canal Systems for. So the next talk will be by Ridhiman Biswas, and the topic of the presentation is Assessment of Human Error Probability in Indian Locomotive Shunting Operation, a study of railway action reliability assessment.